It's great seeing you all back here. Yeah, I'm going to talk about a security model for systemd. The main reason I'm doing this talk is because, in my head at least, it was always clear what the security model for systemd was supposed to be, but let's just say that's not an universally accepted truth that that's the right way. Quite frankly, until I prepared the slides, I never tried to actually think about it, what it actually means, why we're doing everything that we're doing. And my hope with this talk is to make a little bit clearer how the individual security-related parts of systemd actually fit together and why they exist in the first place, right? Because, Linux is this historically grown thing that added this and that and everything else. They had a billion of different security features, and it's all very random. It's not clean. It's just this huge collection of building blocks that sometimes work together well, sometimes don't. But I hope to explain with this where I, at least, would put the emphasis on security, like which building blocks I think actually matter. And then everything that's not mentioned here is probably the stuff that I don't think matters so much. So let's start out with what is actually a security model, right? I have been using this word for a long time, always assuming that I knew what it was. When I prepared my slides, I looked it up on Wikipedia. What does it actually mean? And apparently I had no idea, and nobody else really has either, because the definition there is a computer security model is a scheme for specifying and enforcing security policies. A security model may be founded upon a formal model of access rights, a model of computation, a model of distributed computing, or no particular theoretical grounding at all. And I like that, because it basically means I can make this into whatever I want. That's kind of nice, right? I can just pull something out of my hair, and it's a security model, apparently. So, but of course, let's not do it that way. But yeah, so let's get started. Let's first talk about the scenario we are in, right? Systemd is this basic component of today's Linux operating system. But before we think about threats, let's figure out in which world we actually live here. So the first thing is today's systems are typically always connected, right? I think almost all of them are, even the ones where we do not really think about them being connected, like cars and things like them, effectively already nowadays always are, already simply to update the software in regular intervals. Today's systems are everywhere in physically untrusted environments, right? It's not that that there are only computers in the cloud or something that are securely shut off at a secure location, but they're everywhere, right? Everybody carries around digital devices, and there are many, many digital devices in the public environment that need protection. So they are always and continuously exposed, right? So it is absolutely essential we talk about security to protect them both from attacks on the network, but also locally and physically. So what are attack targets? When we talk about security, we need to think what's actually being attacked here. It could be the system, for whatever that means, right? The whole thing. It could be some specific parts of it, like unprivileged user code, right? One user attacks the unprivileged user code of another user on the local system. It could be privileged user code, right? You have unprivileged user code, and it tries to get control and make privileged user code execute something it wasn't designed to execute. It could mean attacking the kernel from user space, right? This is a primary target of what people do. So there are millions others like this, right? But we need to know what's being attacked in order to defend those parts from whoever is attacking that. There are also different goals in what can be attacked. There's data exfiltration, key material exfiltration, which is kind of the same thing, but it's a little more relevant data. It's about backdooring. It's about DOS. It could be a lot of other things. Stealing resources. It might be a simple thing. I think, we need to think about all these things, what we actually want to avoid, because the protections that you enforce are quite different, right? For stealing resources, for example, you need encryption. But for DOS, protection you don't really, right? Like you need something else. You need to make sure that nobody can subvert your system and use it for its own purposes. So yeah. Then the attack sources are also something to think about, like where do the attacks come from? I mentioned this earlier a little bit, like they can come from the outside, meaning the network, the internet. They can come from the outside, like physical, right? Like this is, for example, a car, or I don't know, like a ticket booth here at the local transport authority. So if somebody just walks up to a machine and does stuff to it, they might get immediate access to money and whatnot. So it can come from inside, right? Like you have a rogue container running in a system, and it wants to elevate its privileges, like get privileges as like root or even kernel privileges. It can come from inside from a VM with a little bit better isolation than container, but it's also something we need to protect. It can come from the inside that it's just regular unprivileged user code, right? Like somebody installed, I don't know, Emacs, and the Emacs package wasn't as secure as they thought. It can also come from inside web browser, right? Like some JavaScript code download from the web manages to break its sandbox or something like this. Of course, there are a couple of places this comes from. Not all of them are relevant to systemd. Like for example, you know, we don't do anything about the sandbox of a web browser. I'm not interested in this problem so much. But at least we need to understand that the attacks can come from everywhere. So I think this one is now like probably the most important slide of all the slides I have in this deck, because depending on where the attacks come from, and in particular what the intention is of these attacks, we need different approaches to have a comprehensive way to avoid them. Like the first one is frustrate attacks, right? Like make them impossible, right? Don't even allow the attack to happen, and everything will be good. It doesn't always work that way. Well, you know, like that your software is vulnerable is inevitable. We have to accept that. So if an attack was successful, we need to limit exposure, right? Like this is the idea of sandboxing, right? Like if you have a sandbox that works correctly, if your system is exploited, they might do bad stuff inside of that sandbox, but hopefully not outside of it. It's about observing attacks, right? Like you want to know. Right, like you want to know not just if the attack happened, but also you want to know if an attack could have happened because your software was vulnerable. It's about undoing attacks. I think this is a really important one, right? Like there always needs to be a clear way how you reset that system, right? This is not so important, let's say, for containers or VMs, because the way how you deal with that is you just delete the VM and container if you have the suspicion it got exploited and just create a new one. This doesn't work that well with physical devices, though, right? Like you cannot just delete a physical device. You have to reset it in some way. So I think, yeah, this is also important. We need always to have something like a factory reset that we can return to well-defined state and know sufficiently well that at that point it's not exploited. And then there is the other part, track vulnerabilities, right? Like all the stuff above is about attacks as they happen or as they happened. But ideally you want to know in advance that something is vulnerable. So yeah, I call this flout, right? Like F-L-O-U-T, frustrate, limit, observe, undo, and track. And I think in systemd we need to do something about all 5 of these. What those are, we'll see later. A little bit, by the way, if anyone has questions, I'm actually fine with if you interrupt me. So go ahead if you have any questions, just raise your arm and we'll try to deal with it right away. Let's talk a little bit about attack mechanisms, right? This is actually not so much the interest of my talk here, like how you actually exploit software, because you know that's like there are millions of talks about this. But just to list them, like there's exploiting memory accesses, there's exploiting races, exploiting logic errors. I think in particular exploiting logic errors are actually the most interesting ones, because the other ones you can address somewhat if you use a better programming language, right? Like you know the Rust in a way, for example, is an answer to the first two, and there are so many tools dealing with the first two. Like even if you, as a C developer, they're static analyzers, and they actually work really, really well. Like in systemd, at least, you know, the vulnerabilities that we ever have in systemd are never really so much in the first 2 categories. It's always about logic errors, right? It's like about us not being able to think correctly. It's not about just making mistakes in memory management or something like this. But again, this is not really what the talk is about. Like, I accept that, yeah, there will always be vulnerabilities. There will always be attacks. We need to make them very, very hard, and we need to be able to react to them. Just generally, Linux is a really complex beast, right? Like, and particularly when it comes to security, because there are so many different security components in there, right? Like, there's the original Unix model with UIDs and GIDs. There's SL Linux. There's user namespaces. All that stuff. And yes, complexity doesn't actually help security, right? So ideally, if we do a security model, we should do it comprehensive enough on one hand, but on the other hand, still not have rely on a million of different components to achieve that, right? That is it's a difficult thing, right? On one hand, you want really good security. On the other hand, you don't want to make the system too complex, because if you do that, you have less security, right? Like, it's about finding some middle place there where you can be reasonably sure that you covered all the grounds, but also didn't necessarily do even more than you have to. This is an excessively complex problem, because Linux was never designed from a clean room in a smooth, elegant way. It's always this historically grown thing about how old is Linux now, 40 years or something, where everything is in there and nothing is in there, and if you want to use it together, it's your problem. So there's also, in the individual security measures that you actually focus on, I think it's highly relevant to prefer universal security mechanisms over fine-grained ones, right? What do I mean by that? It's like, it's always interesting finding general rules that always apply and implementing security policies for that, instead of trying to find individual security policies that apply to a certain project, right? So effectively, what could that mean? Let's say that a universal truth, I have some slides later about this, could be device nodes shall only ever be allowed in /dev. Right. This is a very simple security policy, right? Like, it's a universal truth, I think, on a system. Doesn't apply to any specific hardware, but this is not how many of the security mechanisms that we have in Linux are built, right? Like, because, for example, with the SL Linux, you ultimately write a policy individual for each daemon. And in that daemon, you would then list, it may not create device nodes or something like this. But I think this is a much less interesting thing, because it's more fragile, right? It's much easier figuring out universal truths and enforcing them system-wide on every container, on the host, and things like that, because then you have, but this is hard, right? Like, I think fine-grained stuff it might be useful, but it's also way harder to understand, right? Like, because you have to always look at every single individual service individually and figure out what's right for that. Even though, of course, nothing on Linux should be able to create device nodes, except maybe udev and temp files, but also not outside of /dev ever. So I call those universal truths. There are a couple of these that you can come up with. There are a couple of them that I came up with. I think it's really good, figuring those out and enforcing them system-wide. It's one other thing that I think is really important is we should try really hard to isolate components into separate worlds. I use the word worlds here. You can replace that by containers or sandbox or something like this. On purpose, I use a word here that isn't used that much in the Linux world so far. But to me, what worlds are that containers and sandboxes and namespaces and what all those kind of things aren't, is for me, I think a component of the OS, if it lives in a separate world, then this doesn't just mean that it doesn't get access to what's outside of it, but it doesn't even see what's outside of it, right? So to keep the complexity of these sandboxes small, it's good if all these other objects are not even visible, not even something you have to think about controlling access to, because they are not there, right? So I think this helps with complexity a lot, right? Like, because if you just say right away, your service lives in a separate world where it doesn't see anything else except maybe for the stuff you actually want to allow to it, then the security rules can be way, way simpler than trying to do the reverse. So worlds in this case are combinations of files that work together. wow, somehow the second part of that sentence got missing. Which means, like, yeah, so to me, worlds are really about, like, a bigger picture, right? Like, it's not about individual inodes, controlling access to individual inodes. It's about always controlling access to combinations of things, like whole sets of inodes and how they're used together. Worlds, to me, is both about isolation and about visibility, right? Like, so that it's the objects aren't even there, right? Like, which is different from, like, let's say, security policy with SLinux, right? Like, SLinux has all this infrastructure, but basically, if you take a classic SLinux system, everything still runs in the same world, sees everything, it just doesn't get control to it, right? So, yeah. What worlds, I mentioned this earlier, what it could actually mean in real life, it's containers, it's service sandboxes, and these kind of things, right? Yeah. So one fundamental thing, by the way, again, if you have any questions, nobody has any questions? I think a fundamental thing we need to think about is about how to model apps, right? Like, because, you know, nobody runs operating systems as much as I would love that just to run an operating system. They run operating systems to run apps on it. The apps are the thing that people care about, and the operating system is a tool to achieve that. So we have to figure out, what is an app? So I think what's really important to realize that today, like, an app is not a executable binary. Absolutely not. It's always a combination of many, many things. Apps are libraries, runtimes, data resources, config files, all that together, right? And if we model security, we need to model apps so that we know how to apply the security to it. So combination of many files and in an atomic combination, right? It should never happen that you do a mix and match, that you have an app that uses resources from one version and resources from another version because they are currently being updated and things like this. So you always want the atomic behavior, because non-atomic behavior is a security vulnerability. OCI containers, Flatpak container images are two ways of modeling an app, and they inherently do this, right? Like, they always pack up the whole thing, right? Like the libraries and everything and so on, so that they can test them together. And because, yeah, the security-wise, it's the right thing to do. Coming back to the term world, each app in this way is a world. So this is too coarse, right? Like, then make it each app a combination of images. This is not so much done, I think, in a container world. People do that too, right? Like, that's what layers are for, but usually they flatten things. But in the Flatpak world, that's pretty common, right? Like, if you want modularity, and you generally do probably, you want to have still coarse granularity, right? Like, so that you do not look at individual files so much, you look at the combinations of files. Another thing that is really important about security, I think, is to think about delegation, right? Delegation needs to be in the model from the beginning, meaning, right, you know, just isolating stuff is never going to work, right? Like, because we live, like, the components need to talk to each other, right? Like, on the server side, the database needs to talk to the web server, or vice versa, or the apps need to talk to each other. I don't know, to, like, the app that deals with Bluetooth needs to be able to deal with the Bluetooth team and things like that. So delegation of access is important for this, right? Like, you want to be able to delegate certain functionality to an app, and even allow that this app can delegate things further if it's nested, right? So delegation is kind of, you know, if you think about things as a scale from isolation to integration, right? Like, on one hand, everything runs on the classic Unix system directly and basically with access to everything. And on the other hand, you have complete isolation. It's a VM. It doesn't share anything like this. Delegation is kind of this thing where you delegate components to that thing to move that slider either from one direction to the other, or wherever you need to put it. So. Services and APIs must be something that can be delegated to worlds, and possibly subworlds, and so on. So it probably should be hierarchical. One more thing to think about is about isolation of provenance, meaning code generally comes from different sources, right? while we like to think that the operating system usually comes nowadays from one provider, like one distributor, whatever you want to call it, not even that's the case, right? Like all the distributions, they integrate software from different sources themselves. So, and in any model, usually you have a concept of apps, where apps also means, yeah, those usually come from a different source than the OS itself. So the fact that they come from different sources also has security implications, because if it comes from different people doing them, like that operate basically at different trust levels, you need to model that. You need to think about, like, do these come from different vendors, projects, stakeholders? And then it would be wise if the security boundaries between your apps, between your components, kind of follow the provenance boundaries, like where the stuff actually comes from. This is like, I mean, this is implied in many of the app models anyway, right? Like this is like, if you look at the Google App Store, this is how it works, right? Like Google owns the OS, and then the apps are owned by other people. But it still is worth thinking about that whenever you mix and match stuff from different sources, you need to think about where the security boundaries lie between that. Talking about security boundaries, something that to think about as well. Security boundaries can be between services. Meaning, yeah, you run one service, let's say MySQL, with certain privileges that it can do certain things, and I don't know, web server with different privileges, so it can do other things, like access on the network, which the first one cannot do, or something like this. So between multiple services, you have a security boundaries. They do different things, and they should not be able to take over the other part and do everything that they can do. Security boundaries can be sandboxes, right? Like, for example, JavaScript sandbox in a web browser. They can be containers are a security boundary. Kernel user space is another security boundary, a pretty fundamental one. Boot phases can be a security boundary, right? Like in a TPM world, you have this thing where you can measure stuff at certain parts of the boot. This kind of blows a fuse for that runtime of the system, where basically they lose access to key material and everything that this key material unlocks, right? So that's also a security boundary. There is a security boundary between user identities. Like UID is kind of the primary way how user isolation works. There is other security boundaries, like code versus configuration versus state. This is a pretty relevant one, right? Like, because code, that means executability, right? Like that you can run that stuff. You shouldn't be able to run configuration, right? Like there's it's a mental distinction, but it is a distinction that some parts are code, some parts are configuration, and some parts are state. And what you can do with each one of them, like mutability, the fact that you can execute them, is different for each of these. So it's a security boundary. It should be kept in mind that if you model your apps, for example, that you isolate these three kind of resources, because state and configuration is probably something that should be mutable, but code should never be, because that's an immediate exploit, basically, if some app manages or some user manages to change the code. Processes are sometimes understood to be a security boundary too. I'm not much of a fan of that idea, though. I mean, there's some parts of Linux kernel that work that way, like kernel keyring, for example. I'm not a fan because I don't think processes are useful for this. But yeah, at least I put it on the slides because people disagree. So let's talk about the technology to enforce security boundaries. CPU rings, so this is like the primary one between user space and kernel space. Unix UIDs, that's the primary one between user identities. Linux namespaces, this is the primary one between containers. TPM PCR measurements are a security boundary, as mentioned earlier. Boot phases. Hardware enclaves, really important one, right? Like TPM in a way is a hardware enclave, but like a lot of, like ARM in particular has really nice hardware enclave technology. So yeah. Security labels, like as a Linux puts, like that's their primary way how to distinguish what can be executed. Let's talk a little bit about code review. No one has a question at this point? You guys need to ask more questions. So let's talk about code review. Code review is a security feature as well, right? Like the classic distribution model, Debian, Fedora, and so on, relies heavily on code review. At least that's the claim, right? Like the idea is you don't have to go around the internet and download software from 500 different people that you cannot possibly understand if they are trustworthy or not. Instead, you go to the distribution where they supposedly did some vetting of the code and you trust that. So it's part of a security model. First of all, I don't think it scales, right? Like we are seeing this because app developers usually want to have a much faster cycle of releasing stuff, and the distributions couldn't possibly package everything that exists in this world. So it doesn't scale; it's too slow, and because there's always this intermediary in there, I'm not sure it's the right model to model the entire world. I think it's important, but it's not something that we should rely on. So yeah, in particular because code review is hard, right? Like it's harder than programming. Do we really trust all the packagers and the distributions to do this comprehensively? I can tell you, I'm not. I'm not saying that out of disrespect for the distribution packagers. I'm just saying that because I know that I'm struggling with doing code reviews. And so I assume that other people are not necessarily all much better than I am on this. And yeah, you never know if the distribution developers actually do it. Sometimes it becomes visible that they don't. Let's hope that those are the exceptions. So yeah, sandboxing and compartmentalization is essential there, right? Like you need to be able to break it down so that you do not have to trust a single entity anymore, but you can avoid the fact that code review cannot work universally. So much about all the things that the one has to think about before doing a security model. Now let's talk a little bit more first about what rules I think derive from that. So I think one thing that I think I care a lot about is that kernel objects must be authenticated before they are realized, right? And it's not just kernel objects, like any object. We should minimize any interaction with data, with objects, with stuff that hasn't been authenticated yet, because that is always where the risk is. We should always focus on images, not files. Like this is the thing that I was talking about, that we shouldn't look so much on individual inodes and security on those inodes. We should always look on security of the whole app image, of the whole image. I think one important part is we should measure everything in combination again before we use it, right? Like Linux kernel has the concept of a superblock, which is basically one instance of a file system. So I think it's essential, it's not too useful to look at individual files so much. It's always, we need to look at the combination of things, on the worlds. We need to compartmentalize, to sandbox, to isolate everywhere, right? Which is not how traditional Unix worked, right? Like everything worked in the same sandbox, in the same environment. I think the comprehensive factory set is a must. In order to be able to always bring the system back into a defined state, factory set is not an afterthought. It needs to be in the system right away. And we need to really protect our security boundaries, right? Like we need to think about what can break security boundaries, and we need to put enough security on it so that we always authenticate properly, which is actually kind of hard. On the other hand, I think a good security model needs to be actually usable, right? And in particular, as most of us here are hackers, we kind of like hacking our devices. Hence, breaking glass, by which I mean basically that there needs always be a way how, with all the security protections that you have, you can also enter a mode on the device after authentication or something like this, where you actually can interface with the stuff, look it around, make changes temporarily. But yeah, debugging matters. Authentication must be checked, maybe a locality check, by which I mean, that you must be local in front of the computer. And this must possibly invalidate data, right? Like you should not be able to break glass and through that be able to exfiltrate data that you aren't supposed to be. And it needs to be, and this is absolutely key, be a measured event, right? Like so that even if you might be allowed to do this, there needs to be a trace of it afterwards. So, yeah, security great, but let's always think it was breaking glass in the as well. Then there is. I also want to talk about stuff that I think are mistakes, right? Like figuring out what you want to do is one thing. Figuring also out what you don't want to rely on is another thing. So I put up, like, I mean, I think there are many misdesigns in Unix and Linux, but for security, let's focus on this. Like, one of these are suite, like the suite bit on files, you know? I think it's a terrible way how to do security handling, right? You know, the thing where basically you fork off some binary and that binary magically gains additional privileges. The fact that you drop privileges and this thing can then acquire privileges again and still run under half your identity, under half your runtime parameters and everything from your security context, I think is an absolute misdesign. We should not do this. Not in 2025 anymore, 2026 anymore. We should, like, there are better designs. There's IPC, right? Like, where you do not inherit the context from whoever wants to do this stuff, but you just execute on behalf of somebody else one privileged operation. I think capabilities are a terrible thing too. I mean, they're kind of necessary because Linux works the way it is, but they're also, I think, a design mistake. You know, process capabilities as like in capsys admin, if you know this stuff, right? In particular, capsys admin is a terrible one because it's like this grab bag of, like, it's supposed to split up privileges of the super user, but then there's one privilege that is, like, one capability that is so much bigger than all the other one that it's an useless separation. I mean, it's not entirely useless, and we make heavy use of it in systemd actually, because we do limit our capabilities for all long-running services, but I also think it's a crap idea, crap design, and we only make use of it because it's there and it's really basic, and you cannot even turn it off in the kernel. It's really, you know, the part that is bad about capabilities is also the fact that they're file capabilities, so it's another thing, another model of Zuid, and Zuid was bad, so capabilities are bad by extension. I think another, like, you know, one of the Unix core designs that people always preach are everything's a file. I think, first of all, it's not true, but secondly, you know, where it really is messy is because there's certain kind of objects in the Linux kernel that are not inodes, right? So like System 5 semaphores, System 5 shared memory, all these kind of things, where they basically separate kind of object with a separate set of access control. And it's terrible because, you know, for inodes, like everything that's an inode, everything that can have a file descriptor, we at least know how security works. It's hooked up with almost all of our security infrastructure. It's not the case for System 5 semaphores, shared memory, and a couple of others, because they are this separate thing that were designed in a different time and have completely different security. It's terrible. So netlink is another one. I hate it because it's like there's no, like, it has completely different, like it's another syscall API that has completely different rules on everything. So now let's be concrete. This is kind of the last part. So I think it's essential. Let's sandbox all our services. This is like, you know, the L from the flout slide. This is, what was L again? Limit exposure. Then layered dm-verity and signatures for apps. That is F. What was F again? Frustrate, right? So dm-verity means basically that you cannot modify the images ever, right? Not offline, like physically when you access the hard disk or something, simply with a screwdriver and put it into some other device, and not online. Yeah, so no kernel objects beyond the block device itself become realized before the authentication happens. This is one of the fundamental things that I see there. It's very important to be able to erase partitions, like writable partitions, to erase the TPM, for example, via systemd factory reset. This is the undo, right? So that we can get back to a defined state. I think we need to measure everything. That's both O for observe, meaning that you always need a ledger so that you can figure out in afterwards if you installed bad software, if you installed vulnerable software. It's also T. What is T again? Track so that you know like the vulnerabilities ahead of time or even afterwards, even without that having necessarily been in attack, figure out where the software ran. One universal truth that I think is very, very fundamental: we should really try hard to do writable XOR executable mounts, right? Like file systems should either be mounted writable, so that you can modify them, or they should be mounted executable, right? Like so that binaries can run off them. Never in combination, right? This is the fundamental truth. If we implement that through the whole system, we have a much more secure system because we know people cannot just drop an individual shell script or something or executable somewhere and run it because it's either writable or executable, but not both. Another universal truth, I already mentioned this, device nodes only in /dev. Another one is universal truth, SUID and fcaps, like file system capabilities, are bad. And we can, like, I put here in the brackets here, like technology that we can use to turn this off. Like with PR control, we can actually get rid of them entirely. And then there's LSMBPF. Another universal truth is super blocks must be in memory, encrypted, authenticated, or prohibited, right? I think we need to think about that every file system that is mounted needs to be one of those four, right? And it should not be anything else. Like in memory, meaning something like procfs, sysfs. Encrypted means something backed by dm-crypt. Authenticated means something backed by dm-verity, or simply prohibited, right? Like only if we do one of these, we can always guarantee that it's in a sane state. We need to do measurements of boot phases, like the fuse blowing and a staged boot. This is frustration and observation, right? Like because we know then afterwards what happened, and we also can make sure that access to certain key material is blown once the boot has progressed. Separation between config and sysx is the security boundary between configuration and code. It's also important, I think, that we use a TPM a lot for fundamental, like for the as an enclave for fundamental key material to get the isolation there. This is again frustration and what was L again? Limit the surface, right? Like because you like if you exploit the system, you will not get access to the keys. Delegation matters a lot, right? Like for me, one of the benefits of the Varlink IPC model is how natural delegation works, right? Like because every service has its own socket, you can bind mount them. So it's like it's for if you compare that to dbus, for example, it's a lot more like individual. Like you could just hand that down. I'm gonna skip this slide. I'm basically bitching about SLNX and audit and IMA. Anyway, there are all my other slides about bitching. I just think we have only less like 5 minutes. I mean, unless somebody wants to see those slides, let's first do questions so that we have done that.
Any questions?
Can I see the slide about ComposerFS?
Sorry? I can show you that one. Okay, now this slideshow doesn't work anymore. Oh, there it goes. You know, yeah. I'll put it on the screen. Like we can talk about this if nobody else has any other questions.
Feel free to disregard this if you don't want to go down the rabbit hole. But I would be curious what you would like to see as a replacement of capabilities if you had the magic wand. If you don't like it, what would you like to see instead?
Oh, so I think capabilities, if they were implemented properly, like, you know, the FreeBSD have this, what they call capsicum or something. If they would implement that, that would be lovely. But, you know, it would be another security model in the Linux kernel. And until everything is rewritten to actually do that, I think that's going to be a really hard sell. But my issue is not with the capability model per se, like with the theoretical model. I think it's a fantastic model, and we should actually, like, it would be great if Linux worked that way. My issue is with the actual implementation in Linux, because the capabilities, they like, first of all, they are not assigned to a file descriptor, right? And secondly, they're just completely weirdly separated from each other, right? Like, because everything is in capsys admin, and all the other ones are not so interesting. So, yeah.
Other question.
When will you enable the now new privileges flag in systemd?
Well, I mean,
these are really gone, and distributions need to enable the other ways to do the work.
So yeah, I mean, you see here like universal truths, like killing suitbacks, like the PR control. That's what I meant with the NNP thing, right? Yeah, you know, in systemd you can already turn this on, right? Like in systemd it does not have suit binaries, it does not have fcaps binaries. We do not allow that. Like if anyone sends us a patch with a suit binary or fcaps, I'm sorry, I will refuse your patch, right? But it doesn't mean that the rest of the system works like this, right? Like there are certain people like you, for example, who are trying to do something about SUID and things like that. But I think definitely it should be the goal, at least in well-defined systems, just let's get rid of it. I think we are very close. Like for example, if everything you run is inside of containers, I think we could easily put together an LSM BPF based security policy that would basically say disallow SUID on the main namespace, but maybe still allow it inside of the containers, so that you still get your compatibility with all the garbage that people have deployed that relies on it. But on the other hand, you know that the host system itself at least is protected somewhat. So yeah, it's something that I would like to add to systemd actually, so that we can do something less absolute.
Right. Well, that's all the time we have. So let's thank Leonard.
Thank you.